you hadn't noticed, gives you some idea of how huge these crystals are. It's a cave that I don't believe they allow visitors to go to because the crystals are very vulnerable to the humidity from breath. But it's just incredible. Those were made over hundreds and thousands of years, slowly forming those crystals. We'll talk about how those are formed in this unit and understand what some of their properties are. Chemical bonding, how atoms get together. All right, me, the teacher. Perhaps one of you gentlemen would mind telling me just what it is outside the window that you find so attractive. So take a moment, look at this, and figure out why those metal ions are so attracted to the window. Okay. This is showing ions being attracted to each other without much control. But what I think is funny is the relative sizes are all off. You know, we could talk about the trend in size of ions and everything, but it's fun nonetheless. I'm hit. I've lost an electron. Are you sure? I'm positive. Oh. All right. Why do atoms form bonds? They do it because it's energetically better for them to bond with another atom in most situations. They get lower energy, so when they form that strong attractive force between atoms, they release energy typically and become more stable. They often do it to achieve a stable octet, which is that 8 valence electrons in most cases. Stability is reached by either they can transfer electrons, which means an ionic bond. They can share electrons, which are covalent or metallic. We're going to talk about how those two share differently. They hold together because if they get close enough, there's an attraction between the nucleus and the electrons of their own atom and the opposite atoms. Now, there is a repulsion between the two nuclei, so the attractions have to be greater than the repulsions for it to be a stable bond. Okay, we need to be able to represent those valence electrons, so we're going to show dots. You probably saw these called Lewis dot structures in middle school, and you have as many dots as you have valence electrons. So lithium, being an alkali metal, has 1 dot. Boron, being in group 3A, has 3 dots. Now, often we think of the first 2 electrons as being the s orbital electrons, and they're often shown together. And then the p orbital electrons are on the other sides. There's some other things that happen, so you want to be flexible, but that's how they're often shown. Nitrogen, group 5, so it's got the 2 s electrons and then 3 valence electrons that are in the individual p orbitals. Fluorine has 7, halogen. Beryllium has 2, it's an alkali earth metal. Carbon has 4, and interestingly enough, carbon doesn't show S2P2 in a typical way. We show them as having 4 individual electrons because these electrons do something called hybridization. I'm going to write that down so I can find. Try that again. The B. So the electrons, instead of having S2P2, they change to have 4 identical electrons. So the S and the P kind of morph together. We call them sp3 electrons. We'll talk more about that, but they just all act the same way, and it gives carbon a lot of cool properties. Oxygen has 6, and neon is full of 8. Okay, there's the 3 different types of bonding that we're going to focus on. The first one we're going to talk about is ionic. This happens when the ions are formed. Metals form cations, non-metals form anions. I like to think of that being a cation. It's hard to draw. Anyway, my cat that's positive. And then the anions poorly drawn ant, but the cat is better, it's positive. They form crystalline structures. Ionic compounds are always solid at room temperature because the ions are so attracted, they make that rigid structure. So they occur by having sodium lose an electron, sodium chloride, because chlorine wants to gain an electron. Once they form the ions, they're really attracted to each other. And here you can see what happens to the electrons. Okay, it's an electrostatic bond, just like what happens when you rub your feet on a carpet and then spark jumps from one place to another. It's the same kind of force that holds atoms together in a salt. Okay, so that has given them a specific set of properties. They have a crystalline shape. They are very hard and brittle. Notice how when you stress a salt crystal, you're going to end up with cations next to cations and anions next to anions, and then they will repel and shatter. So one of the properties of ionic compounds is that they shatter. They have a very high melting point and boiling point. And when they are dissolved or molten, they can conduct electricity because those ions are free moving in water. And if you have free moving charged particles, they'll conduct electricity. Okay, and they're usually very soluble in water because water can attract to the ions. Okay, so in order to make an ionic bond, there is energy absorbed and released. You have to form the ions by having the electrons moved, and that is endothermic, even though it's often spontaneous. Energy is released when the ions are attracted to each other. The net energy absorbed or released is called the bond energy. The lattice energy is sort of the opposite. It's how much it would take to pull them apart. So when they come together, they usually release energy, exothermic formation, and then when they're pulled apart, you have to put energy in. It's often an endothermic process. The factors that are important in how tightly a salt holds together are the charge on the ions, how much are they attracted to each other, and the size of the ions. So for example, if you look at 2 different compounds, magnesium oxide or lithium chloride. Magnesium, alkali earth, has a +2 charge, and oxygen is a -2 charge, based on what they'll do when they become stable. Lithium is a +1, and chloride's a -1, or -1, sorry. This +2 and -2 has a stronger charge, stronger attraction than +1, -1, because there's more charge difference. So when you form these ions, magnesium oxide releases more energy and also takes more energy to be pulled apart. It's got the higher lattice energy. What about lithium chloride and potassium chloride? Both of these are +1, -1 ions. So if it's not the charge, then it must be about the size. So which one's larger, lithium or potassium? Take a moment. Okay, size increases as you go down the column, so potassium is larger. And chlorides are the same. And so since potassium is a larger ion, it's going to be farther away from the chlorine, bigger radiuses. So you're going to have more attraction when they're closer together or when they're further apart. Answer is lithium chloride. The smaller they are, the closer they are together, and therefore the higher the lattice energy. The harder they are to pull apart, which probably translates into a higher melting point. Okay, covalent bonding makes something called molecular substances. These, instead of transferring electrons and being held together through electrostatic charges, are sharing electrons and sharing orbitals. So if we show their valence electrons, the blue ones are carbon's electrons that they originally had, and the pink ones are the hydrogen's electrons. So they overlap the orbitals and stay together. Now this happens because they're more equally able to hold on to their electrons, so one isn't electronegative enough to take an electron away from the other, so they share instead of transferring. Okay, so molecules have fundamentally different properties. They have a lower melting point in general because the molecules stay together, but one molecule is not as attracted to another molecule as salt ions are. They have low boiling points. Think about water or alcohols. They don't conduct electricity because they don't have any free moving charged particles. They're all the electrons are accounted for and shared in a molecule. Now there's an exception to these properties, which is called covalent networks, which have very high melting points. Those involve diamonds or graphite or buckyballs, which we'll talk more about later. Here are some pictures of how those are bonded together, but you can see instead of discrete little molecules, they're bonded in 3 dimensions and therefore would be much, much harder to melt. Okay, last type of bonding is metallic bonding. And as we talked about in class, they have only 1 or 2 valence electrons. So when metals are bonded to other metals, that low ionization energy leads to them being able to share those electrons communally. So one atom's electrons become another atom's electrons, and the electrons just kind of move around from atom to atom. They're termed delocalized, and that gives them a lot of the properties that we associate with metals, such as they have a high luster because the metals can be polished very tightly, very intensively. They have a very high melting point, not as high as salts, but do have a high melting point. So again, the attraction of the ions. They are hard, they're highly ductile and malleable. I like this little animation because it shows how metals are more flexible than salts or molecules in that if you move a nucleus around, you're able to then have the electrons just flow wherever they're needed to balance out the charge. They have a low specific heat capacity. Generally, they conduct energy really well, and they are awesome electrical conductors. Again, free-moving electrons. Alloys are a combination of metals so that you can get the best of both worlds. It's a physical mixture, but it does combine their properties. Alloys often have superior properties to those component elements. So most things we see that are metal are not pure metal. Here's some common alloys. Stainless steel, which is iron, chromium, carbon, and nickel. Sterling silver, silver and copper. The copper helps make the silver less prone to tarnishing. 14-karat gold. You wouldn't want pure gold because pure gold is so soft it would bend and deform and wear away. And brass or bronze, which is a mixture of copper and zinc and a few other things. Okay, quick review. Pick which of these diagrams is ionic, metallic, or covalent. All right, if you said covalent here, ionic here, and metallic here, you are correct. All right, thank you. This concludes our semester 1 first Vodcast.